Okay, so welcome to this video, which is the first of a few videos on our main topic for this week, which is hashing and hash tables, which is probably one of the main data types that for sure you want to be familiar with, for the fact that it is a thing that's actually used in database storage. And conceptually, at least, I mean, we're not going to do the full the full grown-up version of how enormous databases are stored, but strategically, it's a lot of these same ideas that are actually used in real life in order to better organize data. So this is really going to be all about figuring out a good way to structure the data and what makes the most sense in terms of organization for sorting and searching and all that good stuff, and adding and deleting and our usual operations. So before I get into material, I'll just point out, I don't know when you're listening to this video, but ideally you are on Monday, the 5th, 6th, I'm bad with the dates at this point, 6th I think. There is a lab from last week on recursion, which is due on Wednesday of this week, which hopefully you've had a chance to put a dent into over the weekend, and hopefully you're finding good success with. The last couple of topics we did, classes and then recursion, are sort of more programming concepts or ideas, as opposed to new structures. That we will return to that with hash tables today, but those are two things that we'll use pretty much in every program for the rest of the semester. Recursion and classes, right? The idea of bundling things into a class we'll use on most of our programs. So the big program that you're going to write, that you'll get later this week, is a hash table program on the material that we're going to do this week, and that'll use all of that. It'll use recursion. It'll use a class, because you're going to make a hash table class. So anyway, it's things we did sort of these mini topics separately so that we could kind of focus on just recursion or just what is a class, but are now going to build those into this new topic today, that will start today anyway, hash tables. I'll just also remind you that there is reading, or was reading, for Monday, and another reading assignment for Wednesday of this week. So hopefully you checked out and or will be checking out those, which as usual is sort of the Zybook version of the notes that we're going to go through in these videos. Okay, so away we go then, I think. So let's come back to kind of where we have spent a lot of the semester, maybe not so much in the last week or so, but thinking about organizing data, and in particular, again, a database, which makes us maybe more so think of a large amount of data. How to do this, right? How to do this in the best way is sort of an eternal question. You'd be a billionaire if you have a revolutionary way to store data that is different than what's currently being done and is somehow more efficient, either because it's faster to find data and store it, or maybe it's cheaper, or things like that, right? So data storage, now more than ever, of course, very, very, very important. So let's kind of return to our roots here, and say at the very least thinking about maybe a database that would store all student records. How do we organize that? So we've gone from, maybe if we asked this question last semester, an array was like, ooh, like that's a thing that we could use that stores a bunch of stuff. And that was like, oh my gosh, that's so much better than single variables, right? I don't know how many, there's 2,500 or 3,000 Endicott students. I mean, right, an array made it possible for us to not have to declare 3,000 individual variables. But actually, it would have been even more, because we would have had to do a name, a first name, a last name, a student ID, GPA, all this stuff. So I would have needed that many per student. So, I mean, so tens of thousands, hundreds of thousands of individual variables. But we got smart, right? And even last semester, we got smart and said, well, an array lets you get a whole bunch of something in one command or one line. And a struct lets you design a variable type so that if you say, well, I want something to hold every piece of information that I want to track about a student, I can make an array of structs, which already that's an enormous improvement. But now we're going to crap all over that and describe why that even that's awful, right? So thinking about maybe a database that looks like that, right? An array or some collection of structs, right? A collection of maybe student structs, whether it's a linked list or an array. What about organization? Well, we've done a little bit this semester. Obviously, we learned about sorting, which of course is the process of putting it in order. But is there a natural ordering that we should be thinking about? Well, of course, if I'm thinking about student files, I have many different things that I might want to sort by. So let's say alphabetical, right? That's probably the most common or simplest thing to think about when you think about a list of things. Well, put it in alphabetical order. Okay, well, we could certainly do that. But how much is this really actually saving? Well, I suppose if if I have an array or a linked list, and I put it in some sort of alphabetical order, first, probably by last name, I guess, how much am I saving a lot of time? Well, if it's a linked list in particular, how do I find something in a linked list, even if it's in alphabetical order? I'd still, on average, have to look at half the list to find someone, right? If I'm looking for someone with the last name Jones or something like that, I got to start at the beginning and look until I get to the J's, and then J-O, and then so on, so right? I'm still looking at an awful lot of people whose name is not Jones. And if I'm looking for someone towards the end of the alphabet, I have to look at more than half of the records of the student names. So on average, I'm still looking through half the list to find this. And even with an array, or maybe using some sort of binary searching, sure, I cut down on that, but I'm still doing an awful lot. Log n instead of n, but okay, right. I'm still doing an awful lot of mostly just sort of somewhat blind looking for things. But then, of course, let's ask make the second bullet point there. Well, what if you don't want to look up a student's name? In fact, what if I don't know a student's last name, but I do know their ID number? Well, of course, right, in real life, we'd like to be able to say, well, that's good enough. I can search by student ID number. Well, if you've stored your data in alphabetical order, whether this is a linked list or an array or whatever, and you want to look for an ID number, now this is a completely unsorted list, at least in terms of ID number, which means, again, we did this at the beginning of the semester, I have to linearly search through basically the whole thing. Again, on average, I'd have to look at half of the entries in order to find the right student ID number. Okay, so if I've done anything, it's hopefully to convince you that maybe there's something better that we could be doing to organize our database. So wouldn't it be better? There's many reasons or many things we could do that might make this better. And if you think about real life, you've all logged into a website before, and you all know, of course, that they have to look up your username and look up your password in some big chart or big table or whatever. And of course, you know that they're not probably scrolling through millions and billions of accounts. There is a somewhat more strategic way to do this. So what if there was some way for us to immediately, maybe I should have put that in quotes, but let's say almost immediately, know where in our data structure this student that we're looking for, based on their last name or student ID. So in other words, what if there was a way to sort of look up the location of where the student might be in this table or list, and then immediately proceed to that location? So, So rather than thinking about, we all hopefully have an image in our head. How do we look through a list and find something? Usually we start at the beginning of the list, and we go into a loop, and we have an if statement in that loop that probably says something like, if this is the one I want, stop. Otherwise, go to the next one, right? Or something like that. Well, that's okay. If we don't have anything to work off of, I guess that's the best we can do. And even binary searching still relies on an awful lot of, well, is it in the upper half or lower half? Okay, and repeat. Right, but neither of those strategies involves us ever doing this. Proceed to the location where you will find your data. We don't even know. I mean, that's like a completely new idea to us right now, hopefully. I mean, at least from our programming knowledge. But in real life, maybe this doesn't seem that unlikely, in the sense that when most of the time we're looking something up, or I should say a computer is looking something up for us, it's pretty fast. Now that could be because it's just computers are generally fast, of course, so maybe even if they're doing binary searching or something like that, it's just that it's very fast. But it may also be that because of creative database engineers, there is an ability to go immediately to where your data might be, rather than doing a whole lot of scrolling and searching and scrolling and searching, right? So how might we do this? So if we're just naively approaching this problem, let's at least fall back on what we already know. An array at least has the ability to do this. I can immediately go somewhere in an array, because of course you have slot numbers or indices, right? You can say, oh, go to index 5, and you can literally go right to that slot, right? So if we were going to try to do something where I would again imagine a database where you maybe, let's say, using ID number, that could there be a way for us to go right to your ID number? And the most naive or basic thing to do would be to say, well, what if we use ID number as the slot number, right, or the location in the array? So in other words, I make a big array, and it's got a bunch of slots or indices in it, and I put student number 168297. I put them in slot number 168297. In that sense, when I go to look it up, I meant to go to this slide. In that sense, when I go to find student, I don't remember what number I just made up, 168297, I think. I just go to that slot. And either, I guess that slot could be empty, in which case I might say, sorry, there is no student with this number. Or there's a student record in there. And again, any information that I might want to know about that student is located right there. Name, ID number, GPA, etc., etc. So, I'm pretty sure we've not done anything like this. I'm trying to sort of go back. Maybe the only thing I would say that probably maybe from last semester in using arrays, we did the maze, which I know I don't have to remind you of since we did it in many different formats, but we did the, go find the whatever. I mean, we sort of used slot numbers in that case. Of course, those were locations of the cheese and the other things, the door and whatever else we were trying to find in the maze. And in that sense, we did sort of go right to those locations as opposed to scrolling, right? We didn't say, oh, let's start at the beginning and look for the door, so to speak. But for the most part, we haven't really done something like this where we've actually used the slot number of the array to mean more than just, oh, whichever one. In other words, we haven't thought too much about slot 5 being that different than slot 11. It's just been, oh, okay, yeah, they're both slots. So we just, right. So maybe we're on to something here, and we are. So as usual, we're going to sort of make some good thoughts and guesses, and then probably see them be improved over and over again until we come up with something we like. But this is a good start, right? So at least thinking about arrays are back in our lives, in case you've missed them and haven't been loving linked lists and things like that. Arrays are coming back, at least briefly, for us. So what do we think? Pros, cons, right? Is this a good thing? What's good about this, and maybe what still leaves us a little bit disappointed about the situation? Well, let's see. Of course, this is where I would ask you to give me some pros and cons, but I'll say play along with me at home here and think about this as we fill these in. So, I mean, one good thing, for sure, is that with an array, right, you can certainly go right to a location. You can certainly do that, right? So if I say you're going to search for a student, I really am not even going to use that word search anymore, because now you might imagine we have a menu program running, and one of the options is look up a student by ID number. So the user types in 168962. There is no let me try to find 168692 anymore. If we did this, we would just simply we would look in slot 1686982, whatever number I said. We would just go there. Well, this eliminates the need, of course, to have a loop that says, oh, start at the beginning and keep going and stuff like that. So this is a big pro. This is good, right? That we can go right to a location. Of course, if we are using a struct, right? If this is an array of structs, of course, this does let us store all of the data about that person in that slot. Right, so an array of structs, which is our candidate at this point for how we might do this. So this lets us store all the data about the whatever student or whatever it is we're storing in that single location. So far so good in terms of pros here. And I'll just say one more while we're over here. Maybe we'll add one in a minute. What else is also good about this? Well, using the example that we've been talking about today with student ID numbers, we know that every student ID number is unique. I think you probably know that, right? That no two students have the same ID number. So if I'm trying to think about, oh gosh, what if that happened? I'd be in trouble. Well, you won't, right? ID numbers, and I think this is probably true in most cases of data storage, if you have some sort of unique number like a social security number for a person, or again, right, some other kind of a number that indicates that identity. Any sort of ID numbers are unique. So no two data items will need to go in the same slot. Okay, so kind of as usual, when we list the pros or talk about the things that are good, it's actually kind of like, oh yeah, like this is pretty good. Maybe we nailed it, and this isn't bad, right? This is not too bad whatsoever. But now, of course, let's come to the whole cons situation of, okay, but what's missing or what maybe isn't great about this? Well, just in terms of thinking about kind of some of our ideas from the opening here, I think one of the things that motivated this little thought experiment was, what if we wanted to find someone? Of course, again, we want to look things up by more than one factor or more than one thing. Well, if I use ID numbers to be the slot numbers of the array of where are you in my array, that's great if I want to look things up by ID number, but that doesn't do anything for me if I want to look things up by name, right? Last name, for example, right? Because if I have these things stored by ID number, then alphabetically, of course, there's no rhyme or reason to how that would look, right? My array from top to bottom would have all kinds of, right, I'd have Q's before A's, and I'd have S's after Y's, and right, all kinds of disorganization. So in terms of being able to do more than one factor, as it's usually called, in other words, sorting by more than one thing, this is not helpful, right? So in this case, it's only, let's say, it's only sorted or organized by ID number, not name. So it would be great. Now maybe this sounds greedy at this point because we're just sort of thinking about this for the first time. But if I could have everything I want in this world, I would like it to be able to also be as quick and efficient and by maybe ID by name as well. Okay, so we could think a little bit about how I might try to make that happen. But that's maybe maybe not a con, but a limitation at the very least of something I didn't satisfy here. In real life, now of course, ID numbers are kind of nice because they are unique, but it's also possible that that the thing I'm trying to store, maybe there is not necessarily a unique identifier for each of them. In other words, no such thing as an ID number. Instead, I just have data that I want to store, of which there's maybe no natural choice for, oh, hey, this is something unique about this one. Well then, if I was in that situation, it would be possible that however it is I'm deciding where this belongs, I might have more than one entry trying to go into each slot. So a good sort of human example of this might be if I'm organizing by address. You might say, okay, well, address. I mean, of course, I have to do something about the fact that that's a mixture of numbers and letters, but just put that aside for a second and say, fine, organize by address. Full address, including, city and zip code and all of that. So addresses are unique. But is it true that there's only one entry for each address? And the answer is probably no, right? There's probably maybe, if you live alone and you are the only person with your address, I guess. But most of us have more than one person in our household, which means if I was doing something like this and organizing by address, I'd be in a little bit of trouble because there would be more than one entry that would be trying to be crammed into each array slot. Now, I could probably get around that, but that's at least a limitation right now that let's list that. Right, so one other thing is that if you don't have a unique identifier, or I'll just say ID, you could have, or you probably will have, more than one entry should be in each slot. In other words, you have more than one entry trying to get. So I'm going to cram that in. That says in each slot. Right, so if you have, again, data that does not have a unique identifier for each one. Now, a lot of things do, right? A lot of things when you think about databases, there is something unique. Again, I'll keep going back to this whole username, password thing. Of course, right, usernames by definition have to be unique and doesn't let you pick someone else's username when you're signing up for something. So in that sense, right, a lot of times 2 is not a huge crisis because you usually do have something unique. But if it wasn't, right, if I was using some system where more than one thing could say, hey, you belong in slot 7, I'd have a little bit of a trouble here because there's only space for one of them. Okay, so that's an issue that we'll have to deal with. But now let's get to probably the more serious issues that would be harder to deal with without thinking of a new way of doing this. So one thing that could be occurring is that if you think about, again, ID numbers, maybe they are issued sequentially, but let's say I'm thinking about, Social Security numbers or something like that. Those are not necessarily issued sequentially. In other words, of the billions of Social Security numbers that are possible, we're not using most of them. So if you made an array that was able to hold, 10 billion possible Social Security numbers, we're only using, a couple 100 million of them. So there's an awful lot of wasted space if you think about an array, because you have to make it big enough in order to hold kind of all your possible values. Well, then probably to guarantee that you will definitely have, the right value for anybody who might come along with a Social Security number, you probably have to way overestimate how many slots you need. All right? So, right, again, in most cases, to have unique slots, in other words, to avoid number 2 up here on the cons list, to have unique slots for each data entry, you have what's usually called a sparse, or you need, I should say, maybe you need, instead of you have, a sparse array, and by that I just mean most slots are empty. Even phone numbers, think about phone numbers for a specific area code. There are far more possible 10-digit phone numbers within an area code. There are, or 7, I guess, at that point. If we say within an area code, you can have 7-digit phone numbers, of course. Well, that gives you 10 to the 7 possible phone numbers that you could do. So that's 10 million, I think. My math is right. Okay, lots of numbers. We don't use all of them, right? Why is it that when you want a new number, they're just like, here you go, here's a new number? Why? Because there's so many that are not used. So if I was organizing by telephone number and said, okay, let me get an array of 10 million slots in order to store the 10 million possible phone numbers, what if I'm only using 1 million of them? That means 9 million or 90% of the array is just empty. Well, that's wasted space, right? And again, this is a real actual problem, right? If you're thinking about storing these things, each one of these, if I'm storing a whole telephone account, there's lots of wasted memory there. Maybe so much so that it becomes too clunky and slow to do it this way. Okay, so having to have unique slots for every possible index number could be very costly and very wasteful, and that you need to sort of overplan. And since if this is an array, we know that arrays are not exactly flexible. So I can't be like, oh, I just got a new one, let me just add some space, right? Okay, right, this is the price we pay with arrays, is that unlike linked lists, arrays are not flexible. Okay, so that's a problem. And the last one that we'll list here, which looks like we have a lot to fix, a lot of complaints about this, is one that we don't think a whole lot about yet in our computer science careers, but security is also an issue. So if you're thinking about this database as storing sensitive information, which in many cases, of course, it would be, I don't think I want someone who happens to know your ID number to necessarily know exactly where, or to know, oh, all I need to do is look in that slot of the database and your information is there. I'd be a little bit happier that even if they knew my ID number, they would maybe not know exactly how to find all of my information in the actual database itself. In other words, it'd be kind of nice if I did some encryption, I guess, in a basic way, doing some encryption on whatever data element I'm using as my organizational tool. If I could do something to sort of morph it, I guess, right, or modify it, then if somebody happens to know it, they would at least maybe not be able to know exactly where all of the data is. So I will just say, right, using a data point, right, some data number, as the location of that information is not terribly secure. Okay, you can imagine, again, I'll go back to some account that you, some online or app or whatever that you have an account with. I mean, if your username, which mathematically may be translated via ASCII codes into a number, if your data was located at that number in the database, then anybody who knew, you could just make up usernames. And again, assuming you have some access to the database itself, you would immediately know what username is in which slot, because it would be basically an easy code to crack. Now, not that we're going to probably write things that are all that sophisticated to do this encryption. I use that word lightly. But in real life, of course, you all know that data is encrypted, and that the storage of data is certainly encrypted, and that it does do something like hashing. Now, of course, their encryption tools are going to be far, far, far fancier than the simple ones that we're going to use. But it's the same general idea of saying, I shouldn't be able to locate I, as the outsider, should not be able to necessarily physically locate data in a database simply by knowing one thing about that data. Now, of course, as a customer, trying to retrieve that data, sure, I want the service, the software that I'm using, to be able to look stuff up and tell me, information about a person. But that's only because, of course, I presumably have some account and I've logged in and I have some security clearance, so it's okay for me to be able to look stuff up. But you don't want someone on the outside who's like, oh, gee, I found a username. I bet I could probably just go into the database and know exactly where that username is. That doesn't sound terribly secure. So, right, so we throw that into our list of complaints of something that sounded good about 5 minutes ago, but now apparently we have all these problems, the 1, 2, 3, 4 over there. Okay, so at least to address some of these, let's, and one of the main issues, again, is this whole, what's sometimes called two-factor organization of being able to sort by more than one criteria. It would also be nice, right, which we listed that as one of our cons. Okay, so needless to say, we have not nailed it with saying, hey, just use an array. All right, so there must be something more to this, and there is. So a hash table, which is our main subject of this week, is going to help us accomplish most of the things on that 1, 2, 3, 4 cons list that we just made. So first, what is this? So a hash table is a data type, or it's a data ADT, abstract data type. So this is like a linked list or some of these other structures that we've started to explore. So it is unto itself sort of a concept, an organizational concept. And what's a hash table and what's hashing and all this about? So there's 4 terms here in blue. None of these, I mean, you don't have to, as usual, it's not all that important to be up on exactly what each term means, but I state them here just to sort of give you an overview of what hashing is all about. So there's a key value for each data value or each data chunk, I guess, I don't know what you want to call it. So students, right? So it's all the information about a student. There is one value called the key value that is going to be the representative of that data element. That was a better word, data element. So again, right, for example, any sort of ID number is probably the thing that's used as the key value, because if possible, it's unique, right? Again, maybe it won't always be, but at the very least, this is the thing that we're going to use in order to decide where does this or where should this be stored. So that's known as the key or the key value. The hash table itself is, of course, a table, so it is a database or it's a collection of elements that are all arranged according to their keys. Now, of course, I probably should have put that sort of in quotes because you don't know what that means yet, or we haven't said what that means yet. So, but in this second sentence, what do I mean by that? I mean that the key values of the elements are what are used to determine where they're stored. Okay, so we've got data elements. We want to put them in some sort of a table, and each data element has a key value. That's the number, presumably number, that we're going to use in order to help us figure out where should it go. But now, instead of just using the key value as the number of where we go, we are going to probably do something to that value in order to transform it into a location. So the second 2 terms there, hash value and hash function, together, they sort of go together. So a hash function, let me read that first, is a function. We know what that means. And what does it do? It associates to each key value what's called a hash value. And a hash value is where should this be located in the data structure, which for us is going to be a hash table. All right? So telling the story from top to bottom, again, we have these data elements. Each of them has a key value. We're going to store those data elements in a hash table. But in order to know where that data element should be stored, it needs a hash value, which is quite literally the location of where it should go. And that hash value is going to be computed by what's known as a hash function, which is going to take the key value and do some math to it, or do something to it, to transform it into the correct location for it to move into. And so when you're entering an element, when you're adding to your table, you're going to use the hash function in order to say where should this go. And then later, when you're looking an element up, or maybe because you want to delete something, you're going to once again use the hash function in order to say, well, if I'm trying to delete student record 16892, I'm going to hash 16892 and find, oh, that would be in slot number 11. And I'm going to go to slot 11, and sure enough, it's going to be there or not be there, I guess if it's not if it's an error, but... Right? So the idea of the hash function is this is going to be the bridge between the data value, the key value, and the location in the chart. All right? So a hash function, which usually use H maybe, or F if you want to use F for function, right, is just like a regular math function. There's an input and an output, or a domain and a range if we were back in calculus class, or pre-calc class. So of course the input is what is the key the key value from the data element. So again, probably ID number or something like that. And then the output is where should this go? So just to use a human example for a second here, if we have data elements that are our class, right? There's maybe our student records for our course here, and I wanted to organize these into a hash table. I might do something where I consider birth month as the thing I'm going to use in order to organize where should these data elements live in my table. And so in that regard, or in that case, if I did myself and said, where should I live in the table, I might say, well, let me use a hash function in order to see, based on my record and my information, and I was born in September, I might say, oh, you know what, I should end up going into slot 9 or location 9 of the hash table because that's my birth month. So I can certainly do that, right? That's an example of a hash function that, maybe is probably not, I don't think birth month is probably super secure either, because of course, gee, that's a tough code to crack. May, is that the 4th month or right? Okay, so probably this is not great for security, but I could certainly do that. Right, so that's what we mean by hash function. It's going to take some value from each data element possesses and sort of mathematizes it, right? Or comes up with a way of saying, well, this is where all of those types should go. Now, of course, more commonly, instead of using maybe birth month, we'll often be using the modulus operator. So I think we all remember this, our friend from last semester. So the percent sign is the modulus operator, which is just a fancy way of computing the remainder when you do division. So remember, of course, this equals, when you use the mod, this equals what's the remainder when you divide by the second number. So for example, 45 mod 6 is 3, because I think you can do 6 times 7 is 42, and then there's a remainder of 3. So the modulus is actually a very useful operator, mostly because the range of the mod is always between 0 and 1 less than whatever number you're modding by. Right? So if you mod by 100, for example, you're going to get some number between 0 and 99, because those are the only possible remainders. So we used mod mostly in order to be able to take maybe random numbers and then sort of control how big they could be while still maintaining their randomness. Well, randomness is pretty good in the sense that randomness for security is actually your friend. So if there was a way for us to sort of use something somewhat randomized, that would maybe be helpful in us not being able to predict where something's going to end up. So there's a little bit of an art to this, and we'll talk a little bit more about how do I know which end to use when I do the mod and things like that. So we'll sort of come back to this. But for the most part, and I think in all the programs that we'll write, we'll be modding by some number, some reasonable number that's not going to be too big because we don't want this to get out of hand, right? So we'll probably more commonly be using something like that. So in that sense, right, so what's the structure, just to sort of recap where we're at? So we're going to use an array, probably an array of structs perhaps, or something like that, because we want to be able to store a whole bunch of facets or members of a particular data item. So an array of structs would let us store a full information about one entry, one data member. And then we use hash values in a hash function and hash values in order to say which slot of that array should we go to. Now, I think we've said this already, but I'll emphasize it here as well, is to say an array is the only way that we know how to say go to the right slot. So a linked list, while I think you all know that I'm a big fan of linked lists and think that they're far superior to arrays in many ways, this is one point for the array camp, because this would be terrible to do with linked lists, because if I wanted to say, oh, you know what, I hashed my new data entry and it should go in slot or in the 145th location of my data structure. Well, if I use a linked list, as we all know, the only way to scroll to get to a specific location in a linked list is to start at the beginning and scroll 144, in this case, times until you get to the 145th slot. Okay, so all right, so for sure an array is the way to go with this, because of course I can't ever go anywhere real quick with a linked list. So this makes me sad, so I put a sad face there. But I will be happy, and if you're also a linked list fan, Fear not, because linked lists are coming back in a few slides to save the day on another problem. So let's just mostly wrap up with an example here and motivate what we'll do next time. So if we were in class, I would say, well, let's try this. Let's see if this is a reasonable way to store things. So let's say I make a struct for a student. We've made that a million times, so let me not redo all of that. But let's say I made a struct and can hold all kinds of student data or student information. Fine. And we're going to use the birth month, right? We're going to use birth month as our hashing function. So I'm going to organize our class. So I think there's nine of you all in class this semester. And I'm going to use that in order to be I'm going to use your birth month in order to decide which slot of the array should your student information go into. All right? So of course I make an array I do this, right? Which we all know what that gets me. That gets me an array, which I'll draw vertically. And it gets me 12 slots, which happen to probably be numbered 0 through 11. But maybe you'll excuse me here. I'm going to number them so they line up with real world birth months. Okay, so I'm just going to cheat here and do 1 through 12 instead of 0 through 11. So when I declare that array, I get this. I get 12 slots. Each of them can hold a student, right? So that's why I tried to draw the boxes big. So whatever I'm going to track about a student, I have room to put in those boxes. Great. So right now it's all empty. So I start going through our class, and I start asking, and I'm going to store, the student record for each of you in this array here. And I start and I say, okay, so let's see. I start. It's been a couple of weeks, but I think I remember where you mostly all sit. So probably from me facing you guys, I would start on the left, or for you guys facing me, starting on the right. I think Dylan might be the first person who's usually all the way over towards the door, and I would ask him, oh, what month were you born in? And since I had a little bit of spare time, I looked up all of your birth months, so you can check me if I'm wrong about any of these. But Dylan was born in January, so when I do that, I would say, okay, let me use the hash function, which says, according to birth month, what number slot should you go in? And it would, so January would say, oh, okay, so all of Dylan's information goes in slot 1. Great. And then I would sort of keep going, right? So I think Zach maybe is usually next, and I would ask him, and he would say November. So I would say, okay, I hashed that, and I came up with 11 as a hash value, so I put Zach's information in 11. And as I keep going, I think Eric is usually next, and I ask him, and he says, oh, February. So I put all his information there. As I continue to move around, I think Teddy's usually next, and he is July. So he would say July, great, okay. And I'm trying to remember which order we're usually in. I think Jeff is usually next, I think. And he would say September, which is the best month ever. So Jeff's data goes there. And then I think Luke is next. And he's March. And then Tommy's usually next. And he is May. He's May, so Tommy goes here. And now we all are commenting, hopefully to ourselves, about how remarkable it is that of the first, 7 names, no two people happen to have the same birth month. Until, I think as I work towards the front of the room again, usually Sam is next. And I ask Sam, and Sam says, I was born in September. Okay, so now we pause for a minute here and say, well, this was looking pretty good, because even for the lookup, right, the storage is going pretty smoothly. If I later on wanted to say, oh, you know what, I want to look somebody up, and I have their information, all I would need to do, right, if I'm trying to find Zach, I would say, oh, you know what, I don't need to know anything about him except his birth month. And that would be enough for me to immediately find his record, right? So that part's going well. But the bad thing has now happened, which is that when I get to my, eighth person in class, I get someone who has the same birthday, or same birth month, I should say, as someone else in class. So if I wanted to, of course, I would want to put Sam here. But there's no space because, of course, it's already taken. So the question is, right, so Sam, also born in September, where should her information go? Well, or what should I do, I guess, right? Maybe just a broader question. So this certainly exposes the liability, or one of the big downsides of using an array is that, of course, as we know, for arrays, they are not flexible whatsoever. And I'm sort of stuck here because I say, well, what am I supposed to do? I have two things trying to go to the same slot. I do still like the structure, right? I still want to organize by birth month, I guess. But, I got to come up with some way of dealing with what the book calls collisions, data collisions, which is when you try to have two things going to the same place. Now, there are a variety of ways to do this, and we'll pick up with these next time. But one thing I could do is I could simply say, well, while Sam should go there, since there's no room, one way I could handle this is I could say, well, let me put her information in the next available slot. Right? So maybe, I don't know, one idea would be to put it down here. And say, well, 10 wasn't being used. So, okay, we can do it. We could maybe just say, well, if you don't have space where you're supposed to go as close as you can. Now, that's still better than nothing. That's still, now if I'm going to try to find Sam later, I could at least say to myself, well, let me look at September 9, and then I ask, is that Sam? Now, if it's a no, which it would be in this case, I could then maybe start scrolling and say, well, let me see if maybe she's located nearby. So it's still an improvement, but okay, right. This is probably not the best thing in the world to do, but that's one strategy that you'll read a little bit about. Another strategy, though, which is what we will do next time, is to say, well, while I'm a little bit worried, or I guess I don't know where to put this information, what if I simply did something that will hopefully inspire a thought, which is to say, what if I did that? In particular, what if I did that? Oh, so I promised, I told you, right? We're not going to abandon linked lists for long, because the popular way to handle this situations like these, is to simply say, oh, well, you ran out of space in the 9 slot because you had too many September birthdays. That's okay. Just make a linked list sticking out of the array, and then you can have as many boxes as you want. Okay, so this is going to turn out to be the best of both worlds. We're going to stick with the array. We are going to stick with the array. We're not going to abandon that, because arrays are great for going somewhere quick. But to get the flexibility of a linked list that lets us add and remove, delete data as we need and don't need it, we're going to make actually an array of linked lists, which maybe if I said that a while ago, that might blow your mind, but it's actually not going to be all that complicated for us to do. Okay, so we'll, I think that's, yeah, okay. So so we'll pick up with this in the next video, but this is a good overview of hash tables and hashing and the purpose of hashing and all of that good stuff too. So stay tuned for more on hashing, and of course you're reading about it as well, mostly I think ahead of when you're watching this. So hopefully between that and this, it's hopefully making sense.